Hi everyone, welcome back. In this lecture we're going to focus on coefficient extraction for rational generating functions. Let's remember the rational functions that we already have series expansions for. So 1 over 1 minus x. We know that's the rational function for this series expansion. 1 plus x squared plus x cubed and so on. In other words, this is the generating function for the sequence of 1's. 1 over 1 minus x all squared is the generating function for the sequence of consecutive integers, starting with 1. More generally, we have that 1 over 1 minus x to the k is the generating function for this sequence of binomial coefficients, which come from choice with repetition. How do we know this one? Well, we came up with a really quick way to see why this is true by just counting the same object in two different ways. So what we did was we just said, hey, let's count the number of solutions with xi bigger than 0 to this equation, x1 plus x2 plus ... all the way up to xk equal to n. How many solutions are there to that equation? Well, the first way we counted it was back in lecture 4, and we said, well, this is just the number of ways to choose n from k with repetition. And so there was our answer. But then at the start of generating functions, we said, well, the number of ways or the number of solutions there are to this equation for each value of n can be encoded as the coefficient of x to the n in a generating function. What is the generating function? It is 1 plus x squared plus ... where those exponents are representing the possible values x1 could take on. And we do the same thing for x2, x3, all the way up to xk. So we've got k copies of this, multiply them all together, and the coefficient of x to the n is precisely the number of solutions to this equation. But we can write this in a rational form as 1 over 1 minus x to the k. And so that means that this is the generating function for the number of solutions to this equation, but that's this value. So this is the generating function for these values, and that's what's encoded right here. And so this is fantastic because this means that any rational function of the form 1 over a power of a linear expression, we can get the coefficient for any power of x from it. In particular, if k is equal to 1, then that just reduces down to this formula here. Because with k equals 1, we get 1 minus 1, which is just n choose n, which is 1, and that's this expression. When k is 2, we get n plus 2 minus 1, so that's just n plus 1. n plus 1 choose n, that's just n plus 1. So when k is equal to 2, we get this expression here. So this is just a much more general form. Works for k equals 1, k equals 2, but then also any higher power of k as well. So that's the first observation. We are going to use this all over the place. So we need to know this one. Commit this one to memory. The power series expansion for 1 over 1 minus x to the k has coefficients given by these choice with repetition binomial values. Now with substitution, we can replace x with various things, so multiples of x, negative x, 2 times x, so on. And we can then just update the right-hand side to get the various coefficients we need. So through substitution, we can get power series expansions for lots of things of this form. One further note, and this is quite an interesting observation, on page 422. If we go into Grimaldi, page 422, there's discussion about what happens if we take the value of k here to not be just an integer, a positive integer as we've discussed here, but what if we make it any real number? Could be a negative integer, could be any real number, so it could be a fraction, 1/2. What happens in those cases? It turns out that this formula still holds. As long as you interpret what it means to have a real number in the top of the binomial coefficient. So what does it mean to have, 1/2 choose 5, for example? What does that mean? Well, on page 422 of Grimaldi, he defines what those binomial, those extended binomial values would actually be, and they're defined in such a way to make this result hold for k being any real number. So it's quite an interesting discussion because it shows how to extend these ideas to not just the positive integer case. We're not going to discuss that in this lecture, but I just wanted to point your attention that there is ways to generalize these results even further. So what's the bottom line? Bottom line is know this result. Know this result. We use it over and over and over again. The series expansion for 1 over 1 minus x to the k is given by this expression. Let's go ahead and do some examples with it now. We want to find the coefficient of x to the n when we take this rational function x over 1 minus x all squared and expand it as a series. So let's do that. We're going to take this and we're going to extract the nth coefficient. Okay, so I want the nth coefficient of x over 1 minus x squared. I'm going to do this in a couple of different ways. One, I'm just going to do some algebra with this square bracket x to the n notation. Remember, this just means extract the nth coefficient. And I want to do it this way because you'll commonly see this happen, and you need to be able to know how to work with the notation. It's important because it's not just blindly doing algebra, manipulating and pushing symbols around. We actually have to understand, as in all cases, generally in math, you have to understand what the symbols mean if you are to actually work with them. And this requires it here. What does this symbol mean? It means extract the nth coefficient from x over 1 minus x squared. Okay. Well, in order to do that, what I could do is I could just say, well, I'm going to get rid of the x in the numerator. Because all that's doing is just multiplying every term in the series by an extra x. So all it's doing is just causing my coefficients to shift to other terms. So if I got rid of the x, it means originally I'm looking for the coefficient of x to the n in this expression. But if I divide through by x, then that's really the coefficient of x to the n minus 1 in this expression. So that's what I'm looking for. There we go. So that's what I mean by we need to know what these symbols mean in order to do the algebra with them. I've just gone from this step to this step by using an understanding of what those symbols actually mean. Those have to be equal. And so now what do we do? Well, now we're saying I want the n minus first coefficient of this expression. So we can use that result from the previous page that says, hey, that's just choose n minus 1 from 2 with repetition. And that's going to be that. So this is with k equal to 2. And so this becomes n choose n minus 1. But n choose n minus 1 is the same thing as n choose 1, which is just n. And so there we go. We've got our coefficient of x to the n. It's just n. In other words, this tells us that a of x is the generating function for the sequence 0, 1, 2, and so on. Consecutive integers, but now starting at 0. Let's look at it from an alternate perspective. So an alternate method for solving the same problem. In my first method, I just worked with the extraction function, coefficient extraction function. In this one, why don't we just work with the whole series? I'm going to start with a generating function I know, 1 over 1 minus x squared. That's the generating function for the series 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot. And now the one I'm interested in is the one I get by multiplying by x. So then I just multiply everything by x. So I get x plus 2x squared plus 3x cubed plus 4x to the fourth plus dot dot dot. I'm interested in the coefficient of x to the n of x over 1 minus x all squared. What is that? Well, I look at what I have here. The coefficient of x to the 1 is 1. Coefficient of x to the 2 is 2. Coefficient of x to the 3 is 3. X to the 4 is 4. Oh, even the coefficient of x to the 0 is 0 because there's a 0 sitting out there. So I see that the coefficient of x to the n is n. And so we get the same answer. In this case, I just worked with the series itself. But we can see from this second case the steps that I used in the first case. I really just used the same idea in both cases. For example, what's the coefficient of x to the 4? Well, that means I'm focusing my attention on this term. But if I think about it, how did it relate to the previous line? Well, the coefficient of x to the 4, that's that number there. Where did that number come from the previous line? It came from that one there. And that was the coefficient of x to the 3. And that's all I used up here. I said, hey, the coefficient of x to the 4 in this one? Well, that's just the coefficient of x to the 3 in the previous one. That's all I used there. It's just having an understanding of how the coefficients relate when you multiply an expression by x. All right, let's have a look at another example. We want to find the coefficient of x to the 5 in a of x. So we've got a of x is equal to 1 over 1 minus 2x to the power of 7. If it's of the form something, a constant over 1 minus something raised to the power of 7, something like that, then I'm like, okay, I know how to deal with that. There's this 2x happening there. Well, that's fine. It just means that it's coming from a substitution. So what I'll do is I'll just put grouping brackets around there just to draw our attention to the fact that, hey, this is really just a substitution of the series that I know. So this is going to be the sum from n equals 0 to infinity of, we're choosing n from 7 with repetition, and that's raised to the power of n. What's being raised to the power? That's 2x. So we are just using our main result with k equal to 7 and then also with x being replaced by 2x. So 2x gets replaced here. That's all that's happening. And so this becomes then the sum, n equals 0 to infinity, of n plus 6 choose n 2 to the n x to the n. And so therefore, what are we interested in? We wanted to know the coefficient of x to the 5 of a of x. We got it, because we actually know the coefficient of any n. It's just n plus 6 choose n times 2 to the n. So in the particular case, when n is 5, we get 11 choose 5 2 to the 5. And so there we go. We've got our result. In fact, we got something even more general. We've got the nth coefficient. Now, if you think back to when we first started talking about generating functions, I said, okay, we've got a generating function. We're interested in working out a particular coefficient. Let's say the 5th coefficient of this thing. We can go ahead and we can have Wolfram Alpha do it for us. Eventually, we'll learn how to do this by hand. Well, this is the day. We've just learned how to do this by hand. Here's a rational function for a generating function. We wanted to know the coefficient of x to the 5. We have now worked it out. And in fact, we've done even more than that. We've worked out the coefficient of any x to the n. And we've done it by hand. All right, let's have a look at the next more general setting. And this idea now comes down to, hey, what happens if we are interested in finding the series expansion for a rational function, which is polynomial over polynomial, where the numerator is not a constant anymore, and the denominator may not just be the power of a linear factor. It may involve multiple things multiplied together. So for example, what happens if we wanted to find the nth coefficient for an expression that looked like this? How do we do it? How about an expression that looks like this? Or an expression that looks like this? How do we do it? And the idea is we're going to use this technique called partial fractions or partial fraction decomposition. And what it does is it just says, you're interested in finding the nth coefficient of this? Well, it's much easier if you split that up into the sum of two pieces. One piece that involves only one of the linear factors in its denominator and the other piece that involves the other linear factor. Because once you do that split, we can use our results to extract coefficients from this one and coefficients from this one, and then just add their results together. The idea, this is really built upon the fact that if I have two generating functions and I add them together, then I just add their corresponding coefficients. So if I wanted to know the coefficient of a particular term of this generating function, and I'm able to write it as the sum of two other generating functions, if I can find the coefficients of x to the n in each of these, I just add their results together. What happens if our generating function is of the form 1 over, and then we've got 3 linear factors? Well, we just want to split it up into the sum of 3 fractions. So we're taking this rational function, we're splitting it up into parts. Each part is a fraction. That's where the term partial fractions is coming from. How about if we had, an x minus alpha, one linear factor, and then another linear factor raised to the power of 2? Well, we'd like to split it up into a sum of a few pieces. One piece would involve one of the linear factors. The other piece would involve another one of the linear factors, in this case to the highest power 2, but we also have to include the intermediate powers as well, because worst case scenario is that they could appear. The sum of these three things, the way you would get it is you put them over a common denominator, which is their least common multiple of their denominators, and that would be the least common multiple would be an x minus alpha times an x minus beta squared, so that's this. But there could also be this middle term that involved a lower power of x minus beta that also was in the mix. So we have to include it as well. And then for each of these, we could extract coefficients by just using our main result that we know how to extract coefficient of anything of the form 1 over 1 minus x to the k. So let's have a look at an example. How are we going to do this in practice? We want to find the nth coefficient of c of x. So the first thing to note is c of x can be written as x minus 2, x minus 1. We want to know the nth coefficient. What I'd like to do is I'd like to split it up into the sum of two pieces. This is the partial fraction decomposition step. It's just a purely algebraic step. Take a rational function, write it as the sum of two simpler rational functions. This purely algebraic step is known as partial fraction decomposition. We're going to do it by hand in just a second, but I want to go through the whole problem where I just suppress this step as just something you would do. How are we going to do it? Well, right now, before we do it by hand, I'm just going to get a computer to do this for me. So what I'll do is I'll ask it, do a partial fraction decomposition of this thing. Wolfram Alpha is happy to do it. And the result there is at the bottom. Tells us that we can write that rational function as 6 over x minus 2 minus 3 over x minus 1. And so there we go. We go ahead and we write down those results. So I'm going to write them quite high. 6 over x minus 2, negative 3 over x minus 1. And the reason I've written them high up is because I actually want to put arbitrary variables in there in a moment to actually do the partial fraction decomposition. So what I'm going to do is I'm going to leave some space. We'll fill in the details here, partial fraction decomposition. But since we already used a computer to do that for us, let's go ahead and continue our work. So what we have found is that c of x can be written as 6 over x minus 2 plus negative 3 over x minus 1. And this is great. We've just written it in an alternate form, one that's easier to extract coefficients from. We're almost at the stage where we can extract coefficients. The idea is it's much easier to do it if it's constant over 1 minus something. And so that's the form I want to get it into. So what I'll do is I will just divide out a negative 2. So I'll divide out a negative 2 from that one. And then I'll also divide out a negative 2. I should have said negative 2. I'll divide out a negative 2 from each of those and have them cancel. So we're going to divide out a negative 2 from the bottom. If I divide out a negative 2 from this piece and this piece, then what I just get is a 1 minus x over 2. And then if I divide out a negative 2 from the top, I get a negative 3, and then the negative 2's would cancel. So that's all I'm doing here. I'm basically dividing out a negative 2 from those pieces, top and bottom, and then canceling them off. And we can do the same thing. Oh, that's not an equal, that's a plus. We'll do the same thing for the next one. I will factor out a negative 1 from the bottom. That leaves me with a 1 minus x. I will factor out a negative 1 from the top. That leaves me with a 3 here, and then I can cancel. And so now I've got negative 3 over 1 minus x over 2, and I've got plus a 3 over 1 minus x. Now typically I would go just from this step right to this step and do all of these cancellations in my head, but I'll leave this here as the one example where I show you what's actually gone on in my head. But the later examples I won't fill in those details. I'm assuming you can follow along with the basic algebra we're doing here. Okay, so now we're going to extract coefficients. So I'm interested in extracting the nth coefficient of c of x, and that means I need the nth coefficient of this here. The nth coefficient of that, well, there's a negative 3 out front, and then I need the nth coefficient of this, 1 over 1 minus x over 2. Well, that has series expansion of the sum of x to the n over 2 to the n. So the coefficient is 1 over 2 to the n. And then for the next one, 1 over 1 minus x. I've got the 3 out front already. 1 over 1 minus x. That nth coefficient of that is 1. So maybe I'll just put it there just so we can see. And so what we have is that this works out to be 3 times 1 minus 1 over 2 to the n. And so there is our nth coefficient. If you're having issues following along how I extracted these coefficients, the main idea is to just remember that this thing is negative 3 times the sum of x over 2 to the n. N goes from 0 to infinity. And so when I extract the nth coefficient, I'm just saying, what's the nth coefficient? Well, it's an x to the n over 2 to the n. So that was our nth coefficient, 1 over 2 to the n. And similarly for this one, this was a 3 times the sum of x to the n. N equals 0 to infinity. All right, so that's it. Now I have suppressed a little bit here. What I have suppressed is the partial fraction decomposition step, but I wanted to just take a step back and see the big picture. I want the coefficients of x to the n. So I split it up into 2 smaller pieces. Those smaller pieces are ones I can deal with. So I extract coefficients from those smaller pieces and I'm done. How do we actually go ahead and split it up into those smaller pieces? That's the technique of partial fraction decomposition. The way we do that is we just say, we are interested in finding some values of a and b which go there. And how do we find those values of a and b? Well, the way I do that is I would clear denominators. Taking this expression and I'm saying that I want them to be equal for all values of x. So I clear denominators. Multiply both sides by x minus 2, x minus 1. When we clear denominators, I get an a times x minus 1 plus a b times x minus 2. And then I can go ahead and expand out and I get an a plus b x plus negative a minus 2b. These are supposed to be equal for all x. Now the way to say that is I've got a linear function here. It's got to equal this linear function. In order for those 2 linear functions to be equal, they have to be the same linear function. So in other words, I need a plus b equal to 3 and negative a minus 2b is equal to 0. I compare coefficients of x and the constants. Now I've got 2 linear equations and 2 unknowns I need to solve. I can use elimination. I'll keep the original or the first equation as is, and I will replace the second equation with the sum of the 2 equations. When I sum them up, I get a minus a is 0, a minus 2b is negative b, and 3 minus 0 is 3. And so that gives me that b is equal to negative 3, and a is equal to 6. And there we go. We have found those values. Those were the values that we had Wolfram Alpha compute for us, but now we can see how to compute them by hand. And so there's our process. I want to extract coefficients from a rational function. If the denominator factors into linear factors, then I will just split it up into pieces, one piece corresponding to each of the linear factors, and then go ahead and extract coefficients for each of those pieces. The decomposition, that's known as partial fraction decomposition, and these are the details on how you would do it in this particular example. Let's look at another example. In this case, here's our rational function, 1 over x minus 3, x minus 2 all squared. We're going to eventually be interested in the nth coefficient of this, as it says here at the end. We want to know the nth coefficient. But the first part is to say, well, why don't you do partial fraction decomposition on this and find the values of a, b, and c. So in order to do this, we need to figure out what is the form of the decomposition. There's an x minus 3 term, so there's got to be something of the form constant over x minus 3. There's an x minus 2 all squared. So there has to be something of the form constant over x minus 2 all squared. But there could be something with a smaller power, x minus 2 to the power of 1, for example. That could appear there. So we have to include it. Worst case scenario, it could appear there. And so we include it. And now we go ahead and we find what are the values of a, b, and c, which make this work out. So here are the details for the partial fraction decomposition. We will clear denominators. We get 1 is equal to a times x minus 2 all squared plus b times x minus 3, x minus 2 plus c times x minus 3. So all I did was multiply both sides by this denominator. And so when I multiply this to these sides here, we get the appropriate cancellations, and that's our result. Now we could expand this all out, get a polynomial of degree 2, compare coefficients, just like we did on the last example. But I'm going to show you another way to think about maybe solving for a, b, and c, something that in some situations could be a lot quicker. And it boils down to just understanding what's going on here. I want to know a, b, and c such that these two things are equal. What are these things? Well, this is a function. This is a function. These two functions have to be equal for all values of x. So if I just start plugging values of x in to the left side and the right side, these always have to be the same. So we just make some strategic choices for the values of x to plug in. If I took x equal to 2 and plugged it into both sides, well, then I get an x minus 2. That would go to 0. I get an x minus 2. That goes to 0. So I get a lot of stuff that just disappears. So I get a 1 is equal to 0 plus 0 plus negative c. And that's nice because it tells me immediately that c is negative 1. So strategic choice of x, plugging it in, evaluating, gets these values very quickly. What's another value? Well, if I took x equals to 3, a lot of stuff disappears. So I get a 1 is equal to a plus 0 plus 0. So a is equal to 1. And I've pretty much exhausted my strategic choices of x because the things that vanish are really where x minus 2 or x minus 3 vanishes. And I've used those two values, 2 and 3. So now I just pick a value of x, which makes things easy to work out. So if I pick x equal to 0, I get 1 is equal to 4a plus 6b minus 3c. But I know the values of a and c already. So I get 1 is equal to 4 plus 6b plus 3. Or in other words, negative 6 is equal to 6b. Or b is equal to negative 1. And there we go. We found our values. A is 1, b is negative 1, and c is negative 1. And so that tells me then that d of x, our side calculation, doing the decomposition, now that we've done the decomposition, we are now ready to extract coefficients. So partial fraction decomposition might be something you've seen in other classes. Calculus 2, for example, integrating rational functions. It comes up there. Partial fraction decomposition is not a topic, it's not a technique or a tool that's specific to calculus or specific to discrete mathematics. It is a tool that allows us to take a rational function and split it up into a sum of simpler bits. So whenever you're dealing with rational functions, this is a tool that's lurking in the background that can be very useful to know. And we're seeing how it's useful here. So it's an algebraic tool. It's taking a rational function and just through a process of algebra, writing it in a much more useful way. Now we'd like to extract the coefficients of each of these terms, which means we'd like to write them in a way that it's easy to extract the coefficients from. How are we going to do that? Well, the key idea is I've got constant over linear in that first term. I would really like my denominator to look like 1 minus something involving the variable. So this is where I'm going to divide out by the -3 to get that constant of a 1. So if I divide out by -3 in the denominator, then I just rewrite my expression in this way. -1/3 over 1 minus x over 3. And I do the same thing for the next one. Plus 1/2 over 1 minus x over 2. And the last one as well. Now for the last one, we have to think about what it is we are dividing by. So I'll just fill in a few things here to kind of get the form. So I wanted of the form, constant over 1 minus something, all squared. To get that 1 means I need to factor out this -2. So I'm going to factor out the -2 from each of those pieces. So if I factor out the -2, it comes out like that. But I need to pull it all the way out of the square. So it's going to come out as a 4. It's going to come out as a positive 4. And then I'd have to divide it into the top. So this is what that one will look like. And now we're in a form where we can extract coefficients. X to the n, d of x. What is our nth coefficient? Well, for the first one, it's -1/3 times. And what is our coefficient of x to the n? For this rational function, 1 over 1 minus x over 3? Well, through substitution, that would be a 1/3 to the n. And then for the next one, I get a 1/2. And then the coefficient of x to the n is a 1/2 to the n. And then the next one is I get a -1/4. What's our coefficient of x to the n? Well, this is a 1 over 1 minus x over 2 all squared. Because of the square there, we know a binomial coefficient is going to come up. It's choose n from 2 with repetition. And then we get the 1/2 to the n again from that substitution. And so we've extracted our coefficients. This is -1 over 3 to the n plus 1 plus a 1 over 2 to the n plus 1. And then I get an n plus 1 choose n, so that becomes just an n plus 1. So I get a minus n plus 1. And then we got that 1/2 to the n times a quarter. So that becomes a 1 over 2 to the n plus 2. And so there's our extracted coefficient. All right, so that's it for the first part of this lecture where we did coefficient extraction and partial fraction decomposition in the case where we had a product of linear terms in our denominator. In the second part of this lecture, we're going to look at series division. So what happens if we have, instead of a polynomial over a polynomial, what happens if we have the full series over another full series? How can we divide one power series by another power series and get the corresponding resulting series? That's what we're going to look at in the second part of this lecture. And we'll actually see that it's related to recurrence relations. So thanks for watching, and we'll see you in the next lecture.